Aha, traveling salesman problem, we want to find the minimum tour. Okay, so if I have a minimum spanning tree, then I have some guarantees already about what is the how much I cost, but because it's not creating a cycle or this kind of tour, so I have to do something about it. So the first algorithm makes this kind of silly tricks, but it does give something done. So at the next of this, it has the spanning tree. Now here's an example. So okay, can you do spanning tree for this graph? Okay, you may not see a graph, but now this is first of all, there has to be a connection between every node. So what I'm doing here is assuming that this is just nodes on the plane, and we apply Bird's distance or Euclidean distance. So any node, the distance from one node to each other is calculated by the Euclidean distance. Okay, do you remember what is how Euclidean distance is calculated? If you have two nodes, and if the distance in x, the distance in horizontal direction is x and vertical direction is y, the Euclidean distance is x squared plus y squared and square root of that one. Yes. Okay, so this is the rule how to calculate. So any distance between any point we can always calculate in Euclidean. This is called Euclidean space. There can be other distance. This is not the only one, but this is how the birds fly. If you calculate the distance, if you travel yourself, that's what you calculate. Now, there are other distances. So before going to solve it, just to understand, to connect this to the reality. If I'm now going to the Joensuu railway station, what is the distance there? Now we are somewhere the Joensuu city areas like that. This grid area. Science Park is here, we are here. Then there's a river, there's a bridge, there's a whatever, and the railway station is here. What is the distance from Science Park to railway station? What? 2 kilometers? 2 kilometers? Yeah, could be. But how do I calculate it? By this equation? No, this is actually the shortest path problem in the graph, right? So we have to, So we have to follow this city block and this road network. So we have to have something where you calculate. But let's suppose we don't have any route network. We just have the plane. Okay, let's take a extreme example. Manhattan. Do you know where's Manhattan? New York, the big island, and most of this is the city, this grid structure. So in Manhattan, if you want to go from one way, okay, now let's suppose I'm now 55th Street, and I want to go 78th Street. And now in the 3rd Avenue, I want to go to the 6th Avenue. 6th Avenue, 78th, I want to go here. How do I calculate the distance? Without the road network. Just having the coordinates, the index. So the index is the location. So I have just a number on the plane and another number on the plane. I'm not allowed to cross the blocks. So how do I calculate the distance from here to here? Okay, just to make it more easier, let's assume this is x and this difference is y. No Euclidean. Euclidean distance would give you this distance. Yes, x plus y. It's even simpler than Euclidean distance. But yeah, this is called city block metrics or city block distance. Also called Manhattan distance. So, because yeah, you have to travel both directions independently. If you have to first go to x here, and then the y. You have several choices how to do it. You can go this way, you can go also that way, doesn't matter. But that's the distance. Okay? Now, I will take another example. You remember the 8 queens problem from yesterday, right? How the queen moves. Okay, now let's forget about the queen. Let's take the king. What is the difference of king movement compared to the queen? So queen can move into any direction, any number of steps what she wants. But the king is limited. He can only make one step at a time. He can also have freedom to move any other square, but only one step at a time. Now, let's suppose the king is here, and then that square, and then the opponent have a pawn here. And now the pawn is moving to the down here to the square. He wants to reach this square. Do you know what happens when the pawn reaches to the last line? Promote it to the queen. Or actually promote to any piece, but usually queen. Okay, what the kings want to do is to stop the pawn. It's usually this kind of phrase. You have to actually calculate. When you do calculate that, what is the best move, what will happen? If I eat that, if you take that, what happens then? Aha, what is remaining? One pawn here, my king is here. You have to calculate, is it possible to stop it or not? Because when it gets promoted, you are lost. That's so powerful, this queen that... Okay, so how do we calculate the distance from king to that square? Okay, I will give you a hint again. I have distance that this is, okay, 1, 2, 3. It's 3 from x direction. 1, 2, 3, 4, 5, 6. 6 in y direction. What is the distance from king from here to here? How many steps does it take for king to move from here to that square? Of course it can try to capture here, but it will keep on moving, so it's better to aim to block it here or somewhere before. So the critical distance is actually this one. How much is it? 9? Are you sure?
No.
I don't think I will need 9 moves to get there.
No.
Yes? 6. Yes. It can move to any direction. What I do, I move here 1. I will move here 2. I will move here 3. Actually, I can do 1, 2, 3, 4, 5. Ah, sorry, this is 5. But the answer is okay, 5 in this case. So I move first, second, third, fourth, fifth. Okay, what is the 5? What is in general? If you have x and y, what is the distance? Maximum, yes. So in that matrix, the distance, you have only the 2 coordinates, but the distance is the maximum of these 2. Okay, what this is called? This is called chessboard distance. Okay, also in literature you will find out this is, okay, the Manhattan distance is called L1 matrix. The Euclidean is called L2 matrix. And this chessboard distance is called L infinite matrix. So if you ever come up with this term, now you know what they mean. So it's just a different definition, and you can see. And this chessboard distance, okay, I'm telling you because I like to play chess, right? No. I tell because it's also needed in practice. Okay, I give an example. We have the same company who's making the what is the silicon board, right? Manufacturing silicon boards. And what you have there? Oh, did I tell this example already? No. So maybe or maybe not. Okay. So what they do here, Just tell me, hey, you told us already. So you have this arm that have all the silicon, these conductors you need to put in the board. So it was the travel. I think I told you already sometime. It's a travel assessment problem. You have to put them there, right? And then this arm is just moving, and then you have to just move this board around, right? Okay. So yes, you have to certain number of locations you have to visit and put the conductors there. And you have to make it as fast as possible. Okay, how it is implemented in practice? Okay, yes, it is a travel assessment problem, but what is the distance? So instead of the arm is not moving, the arm is there, but the board is moving. And the board is not moving like that, like it doesn't follow Manhattan distance. So moving from one location to another location, the board is moving. First here and then here, right? No. The clever manufacturer had not only one engine, it has two engines. One moving it this way, another one moving it that way. And if you are moving it this way, would you keep the other engine stopped meanwhile? No, you have two different layers. One of the engine moves the board in this way, other one this way, but they can move it simultaneously. Difficult English word. At the same time. So when I'm moving from here to here, both motors are moving. I'm using chessboard distance. So that's where you will find it actually. So you never know what is the real distance on your data. So usually it's the Euclidean, but sometimes it can be also the chessboard distance or the Manhattan distance. And then if you have complicated machine learning or pattern recognition problem, then you might even know what's your data. You don't even know, okay, it's just some numbers, it's just some spectral measurements there, or it may be some of computer vision's audio signal. And now you have two signals and you want to know what's the distance of these two objects. So this distance of similarity, what you calculate, this is, you don't know what it is. And then you have just some numbers and you have to guess. And then you have the first decision you need to do. Should I use L1, L2 or L infinite? Of course there are other distance metrics, but yeah, so at least if you know what should be used, it would be much better. But now, okay, the next example I will assume that it's a Euclidean distance, but you can, maybe I'm so nasty that I will make a exercise question. Oops, I already made them. Exam question. Well, same example but using different metrics, and then you chat, but it was that, and then you go to the Okay, before I go too crazy, so let's have a 10 minutes break and continue after 18 past.